Hi, in the next 50 minutes, you will learn about object-oriented programming, yes, but you will also learn about what does declaration and implementation mean, arrays, constructors, public and private section and why is important, getters and setters, structs, and a data structure, the static list, that is going to be our practical case, and we're going to end up converting into a basic inventory. You will also have some challenges at the end to prove your understanding. And most importantly, I will explain the reason for all this. Object-oriented programming is the most important paradigm of our time. Formal definition says that it is a programming model that organizes software design around objects that are unique from each other. All objects came from a class. We can imagine them as clay figures and the class as a mold. Objects have attributes and methods. Attributes are the internal variables that the object can store, and methods are the functions of the object. Let's deeply explain this using practical cases. Our first object will be a list of decimal numbers, but in computing we call them float numbers. So we could put anyone at the end, remove some of them, and print them all. Pretty straightforward, right? Let's make the declaration of this class. Declaration means that we are defining what attributes and methods it will have. For each attribute, we define its name and type. And also for each method, we are specifying its name and what inputs and outputs we're going to expect. Void means there is no output. For the declaration, we have not yet defined the internal process of the methods. In C++, the file extension HPPP is for declaration, and CPP for implementation. Implementation means specify the internal process of the methods, and I will do it in a moment. For now, let's create the main function. This is where the program will begin and end. First question, how we can make a list object of a list class? Or first clay figure from the mold? Well, we can declare it as a variable, like this. That's it. List1 is how we name it our first object. This is called instantiate. And what's going on here internally is that we're reserving enough space in the computer memory to allocate the attributes, 10 floating numbers in an array, and an integer that will count the elements we have. This counter should always start at 0. Because the list at the beginning is empty. So how can we guarantee this behavior? Answer: with the constructor. This is a default method that will be executed at the same time the object is created. This is the declaration of the constructor. In C++, it has the same name as the class. Now the syntax for the implementation is as follows. We have the class name, then a colon twice, and then the name of the method. In this case, the constructor has no inputs, and in no case does a constructor have an output. So let's create our CPP file for the list. And the constructor looks like this. Now to access the internal attributes of this object, we can use the following syntax. And now we can assign 0 to the counter as the initial value. And voila! Back to the main. The way we use the methods and attributes of this object is by naming it, then placing a point, and then the member we want. I want to add a new float number to this list, so I'm going to use the addElement method, and this requires the element as input, so let's put 0.4. This is the declaration, and we have to do its implementation. What happens here is that the counter also marks the next available position, because the index of an array starts at 0. So this line allocates the element at the index where the counter indicates. And the next line increments the counter by 1, preparing for the following operation. For a better explanation of the removeElement method, I'll add 7 elements to the list. This method must receive the position of the element we want to remove. delete it from the list, and return it. Going back to the main, I want to delete this 2.2 that is in the index number 2. Remember that this is the third one, but we named the places starting at 0, so we can call it as we have already seen. List1.remove element at the position number 2. So let's implement this. From the element that we want to delete to the last one, for each one, we're going to replace the current one with the next one in front. In the end, the element we want to delete will be overridden, achieving our purpose. But the last element will be repeated. By decrementing the counter by 1 unit, we simply ignore it. It will become a junk value, and everything will continue as if it were not there. Finally, we return the value that we cleared, because we captured it at the beginning. So then, back on the main, we can grab this returned value for printing and see if it works as expected. For that, I'm going to create a function that will receive the element we want to print. I'm going to name it printMyElement. Its purpose is to easily display the element in the terminal. It's a generic way to print. Let's call and pass the deleted element to it as input. I'm going to compile and run this, and you can see that it prints 2.2, which was indeed the number in index number 2. Finally, I'm going to implement the last method. It uses the printMyElement function for each element in the list, as you can see. To prove that everything is in sync, instead of printing the element we removed from the list, let's print the list. We can see that it skipped 2.2 and print all the rest. So it works fine. We can notice that when we name the object and try to access its members, the code editor doesn't suggest the attributes. And that's because it's forbidden, as we keep the attributes in the private section. That means that we cannot access them from outside their own class implementation. But nothing is impossible, and we can, for example, move the counter to the public section. Now the editor suggests it, but this could be inconvenient. Let's imagine that Pepe is another programmer who wants to use our list class for some purpose that actually we don't care about, because it really could be for anything. Note that before he could instantiate and use our list via its methods, and no matter which one he chooses, everything will stay in sync. But now that the counter is public, Pepe can, by mistake, modify it. Assigning a lower value will override active elements, causing data loss. And assigning a higher value will add junk values to the list. In short, something unwanted, because we let Pepe use something that is not relevant to him. So we better keep the counter private again. Now, if Pepe still tried to access the counter, the compilation will throw an error. But that's much better than having unexpected behavior and not understanding why, because he will be able to identify and fix it. We normally keep attributes private, and a common technique to access them indirectly is through getters and setters. The logic of that is to have controlled access. Setters allow users to modify attributes, and getters to query them. It is like a door in a building. If we have one, we can, for example, count who enters and who leaves. Or add some constraints, for example. Putting another code example, we can have a setter that allows us to set a number as long as it is not greater than 100. Access also means read and write. If, for example, we want to make a query-only model, we can disable the setters. If you already understood what was said above, let's do something more exciting. A list of floating numbers isn't very useful, so let's switch to a product description to make this an inventory. First, we're going to create a struct that will contain the product description format in a new HPPP file. Each description will have a name, a quantity, and a price. A struct is very similar to a class. It can also be instantiated and accessed in the same way. But it doesn't have a private section, and it's normally used to store a set of variables, as we're going to do. Now, we want to have a list of 10 products, so let's change its type. We are going to receive here a product description instead of a float number. When we use remove element method, it returns the element we removed. This element will also be a product. Do you remember the printMyElement helper function that uses this method? Because we delegate the printing logic to it, we can adapt it. This will no longer receive a float. We're going to add white spaces between each value, just for better visualization. Don't worry too much about this part. Finally, let's change the float type in the list implementation. That's it for us. Now Pepe needs to do the rest in the main, and use our list correctly. The cause of these errors is the way the list methods are called, with the old data type. Let's start from scratch. Here we're going to instantiate some products and load some data into them. The best option will be with a menu, but for our academic purpose, I will keep it that way, to avoid adding irrelevant complexity, and you can see the timeline of the calls. Finally, let's print the elements, to see that this works as we want. Can you see that the struct follows the same logic as the object? By changing the data type, internally, this works exactly the same. Of course, it changed the size of the element in the memory space, but we don't have to worry about that. That's the magic of abstraction. If you want to become a programmer, you definitely should master it. That's why I have 3 challenges for you. Have you noticed that remove element by the position is not very convenient? Because it won't always be the same. So you can work by adding an ID number to the product description and changing the remove element method so that it receives the ID number of the item you want to remove instead of the position. After the last implementation, can you create your own list method that prints only one product by a given ID? And finally, if we change our product struct to a class, we keep everything in public, we add the constructor and implement it in a new CPP file, you will see that this works exactly as before. But that change doesn't make sense unless we put the attributes in the private section and add getters and setters for each one in the public section. As you're watching, this will require you to implement these methods and also change the way we access the product attributes. The idea is for this to work as before, but of course you can add some kind of control via getters and setters. After all, that's the point. For example, that you don't accept products with a blank name. Are you able to do it? You will find GitHub links to this code in the description. And if you just want a quick approach to the point, bypassing the installation of any C++ dependency and the process of connecting all the files, you can also have links to this code in an online editor, all in one file, where you can, of course, run it to. Answers are included, but try on your own first, please. Object-oriented programming is the most important because it emulates the real-world behavior. Imagine a video game character. It could be an object, and its life label or strength, its attributes. Actions like walking, jumping, or attacking can be their methods that the user can activate via button commands. In an e-commerce, an object could be a shopping cart, very similar to our inventory. And yes, we can have more than one shopping cart and more than one game character. We only have to instantiate them as many times as we need. Internal in memory, we take for each instance enough space. Therefore, each object is independent. Notice that the this syntax we saw gives the object a sense of itself. It is like the pronoun I we always use to refer ourselves. But what does this chunk actually mean? If you try to print just the this part, you will see something like this. What the hell is this thing? It is a memory address, my dear. And that opens the door to an entire new world of possibilities. But we're going to talk about that in another video, so you can subscribe and hit the like. Thanks for watching.